Right, so let's see this case where we have an Atwood machine at an incline. The traditional method we will do first, and then we will see the fast way. I consider that the two masses are the same, 2 and 2 kilograms. That means that the forces due to gravity are mass times g, so they're 20 newtons. I need to do the free body diagrams. So for object A, just because it's an incline, the x-axis should be parallel to the incline, the y-axis perpendicular. The forces on object A are the force due to gravity down, the normal force perpendicular to the surface, and of course we have the tension. Now for object B, we have the force due to gravity and we have its tension. Now, in this case, depending on the masses, we could have both cases, like we can have them moving this way, or if mass A is big enough, we can have the opposite. Now, let's consider, considering the masses are equal, I will see this motion. So the first thing that we do is we do the free body diagrams, and I see that there is a force due to gravity, that it's not on the axis. It creates within the y-axis an angle of 30 degrees. Remember that the angle of the ramp, the incline with the horizontal, is always equal to the force between the force due to gravity and the y-axis here. So the first thing I do is I resolve this free body diagram. Right, I resolve the force into two components, the x component and the y component. And just because the y component is adjacent to the angle, it gets the cosine while the x gets the sine. So by doing so, I find what the x and the y components are. Now I have to go back and see for both objects, object A, object B, the sum of forces on x and y axis. Well, I have an acceleration towards here. I will consider this positive, positive. Let's go here, positive, positive, negative. So that means that the sum of forces on the x-axis will be the tension minus the x component should equal the mass A times the acceleration. So I do know the x component, it's 10, and I do know the mass. And I create a formula with the two unknowns, tension and acceleration again. Now in object B, the sum of forces on the x-axis are 0, no forces there. I have the forces on the y-axis. If I consider this positive, this is negative. So the force due to gravity B minus tension should equal the mass of B times the acceleration. And I know the values, so I create the second equation that has unknowns, the tension and the acceleration. I solve for tension because I'm looking for the acceleration. I solve for tension, I solve for tension. And then just because the two tensions are equal, I make these two parts equal, and I find that the acceleration will be 4a equals 20 minus 10. And I come up with this. The rest is math. Now, going back to the easy way, I do know that the common acceleration should be the total moving force over the total mass. Well, the total mass is 4, 2 and 2, which is here. That's the total mass. I add the two masses. What is the total moving force? Well, the total moving force is actually the force due to gravity of mass B minus the x component. How do I find that? If I follow the tension, I find the forces that go along the tension. And these are the forces that will actually affect the accelerations, the common acceleration. So going that way, I have that the forces are the force due to gravity B minus the tension plus the tension minus the x component, and I have it here. So the total moving force is the force due to gravity P minus tension plus tension minus Fgx, right? Fgp positive minus tension plus tension, which is the same here, plus tension minus Fgx. So actually, in this case, the total moving force is Fgp minus Fgx, which is what I found here, 20 minus 10. When will the acceleration be negative? It will be negative if Fgx, the x component of mass A, is bigger than Fgp. If this is bigger than that, then the two objects will move the opposite way. In our case, that would have happened if the mass A was more than 4 kilograms. In that case, we would see exactly the opposite motion. This going up, this falling. Now, what about if there's friction? Well, if there's friction, and we mean friction here because here we don't have friction, right? This problem was solved with no friction. What happens if we had friction? Well, friction would oppose motion, so it would be like that. That means that here I would have another force friction, and here I would have another force friction. That means that here I would need to subtract the force of friction. That means that here I would need to subtract the force of friction. That means that here I would need to subtract the force of friction. That would be the difference if I had friction. Everything else stays the same.